Hello, everyone. Welcome to this Kolena webinar. We're very lucky to have Anjali here from Rad AI with us today to talk about boosting your ML performance. She's going to talk about her use case. We're going to talk about how to reduce failures and enhance testing. This is we're Kolena, just to establish who we are real quick. We're an AI quality platform. We're all about this idea of rigorous and systematic model quality through testing. We have a conference coming up. I just want to plug very quickly in San Francisco on June 25th, AI Quality Conference. Love for you to join us there. We're going to be expanding on a lot of the themes that Anjali will be sharing with us today, and we'll be doing it with a lot of great guests. So I encourage you to check that out. I'll put this at the end of the presentation as well. The themes for this presentation. So we're going to be focusing on understanding common pitfalls. So we're going to dive into the frequent cases of model failures in ML projects. We're going to learn how to anticipate and mitigate these issues early in the development. We're going to talk about testing methodologies, of course. So discovering testing methodologies that reduce your time to market and ensure your model's reliability and performance. And then, of course, best practices. So best practices in model development. We're going to hear from Anjali about best practices that she's learned, she's used in her career for ML model development in terms of enhancing model accuracy and efficiency. So we're very lucky to have Anjali here with us today. She is a senior machine learning scientist at Rad AI. She has a PhD in biomedical engineering from the University of Texas Southwestern Medical Center, where she focused on deep learning in medical imaging. She also has a master's in bioengineering from Rice. Her specialty is in applying AI to enhance radiological diagnostics and patient care. We'll see that when she talks about how Rad AI is serving the need. She's been at Rad AI since 2022, and she's developed extensive knowledge of the modeling challenges and solutions there, and that's what we're going to be using for our talk today. I'll say a little bit about Rad AI, and then I'll hand it over to Anjali to expand on this, but Rad AI is made for radiologists by radiologists. They're serving radiologists by leveraging their own custom-trained generative AI models. They utilize one of the largest proprietary radiology report data sets in the world to deliver solutions that save physicians time, reduce burnout, improve patient care. The customer base they're serving, radiologists, they're highly discerning because they're specific about the language and terms that they want to use. And if they're going to use AI personalization to help fill in some of that need, they need it to match exactly their standard, their exacting standard in their style. Some of the products where Rad AI has incorporated AI into what they're doing, which is a big part of everything they're doing. They have Omni reporting, which employs these advanced language models in addition to generative AI to create comprehensive and accurate reports. Omni Impressions automatically generates report impressions from dictated findings. We'll see some examples of this from Anjali. And the impression language, critically here, is individually customized to each radiologist in practice, which means that the models have to be trained to perform well across many different individuals. And then another one of their products here, Rad AI Continuity, closes the loop on follow-up recommendations for significant incidental findings in radiology reports. Some of the challenges here, Anjali will expand on this, but this is kind of setting the stage for what the kind of complexity that Rad AI has had to deal with. The dynamic nature of these generative AI models, we all know how they are non-deterministic. You have output that can vary quite a bit. So it requires the team to continuously adapt and test their models to ensure that they don't stop accurately reflecting the unique reporting style of each radiologist. They need extensive testing frameworks to maintain model accuracy and prevent regressions across all of these different customized models. And the complexity here means that you really need to start using custom metrics. You can't use standard evaluation methods because they don't dig deep enough into the performance that we care about here in terms of the customization. Ad hoc isn't really enough. And so you have to become systematic, and this is what Kolena helps to facilitate. And Anjali is going to talk about how she brought that in for Rad AI. Just to wrap up here before I hand it off to you, Anjali. Challenges here is they have to meet extremely high quality standards to build alignment and trust across teams and with customers. to maintain high accuracy to build trust and adoption among their detail-oriented customer base. They have to ensure these high customization levels to match each radiologist's reporting style, and they have to manage large-scale testing, a huge customer base, all kinds of individuals, and they have to maintain accuracy and prevent regressions across all of those. So I'm very excited to talk to Anjali about this today. Anjali, welcome.
Thank you, Skip. Let me share my screen. Okay. I'm hoping that my screen is visible.
Yes.
Okay. Good morning, everyone, and thank you for the introduction, Skip. I'm quite excited to be a part of this since we use Kolena quite significantly in our workflow. I'm going to start my talk by talking briefly about Rad AI. I know Skip already covered it, but I'm just going to cover a couple of important information. And then I'm going to talk about some machine learning model challenges that we kind of face in radiology space and how we kind of evaluate whether we overcome these challenges. So Rad AI was founded in 2018 with an investment from Google's AI fund. We basically currently have products that increase reporting efficiency and quality while reducing radiologist burnout. We have around 110 plus partnership in the US, and we serve more than 3,000 radiologists around US. So we actually offer 4 distinct products that are organized into 2 main ecosystems that are designed to enhance radiological workflow and patient care. The first ecosystem is the Rad AI Omni reporting system. Reporting is a tool that actually leverages advanced language models like LLMs and any sort of NLP models to produce comprehensive and precise radiology reports at remarkable speed. Omni is our flagship product, our impressions feature that automatically generates report impressions from dictated findings that can tailor the language of the impression to each radiologist style and the practice's requirements for a personalized touch. We also have Nexus, which introduces an AI-enhanced dynamic work list that optimizes radiologist workflow by prioritizing which tasks to do quite efficiently. Then we have the Rad AI Continuity ecosystem. Continuity is a product that ensures follow-up recommendations for significant incidental findings that come up in radiology reporting. It's still a reporting product, but it belongs to a different ecosystem because it kind of solves a different problem. Continuity kind of makes sure that the incidental findings that come up in radiology reports are tracked and managed efficiently, thereby closing the loop on patient care and ensuring critical findings are always appropriately addressed for a patient. Each of these ecosystems is actually designed to support radiology practices with cutting-edge technology, and the goal is to actually improve the accuracy, efficiency, and personalized care delivery for patients, as well as efficiency for radiologists. So for the presentation part of our chat today, I'm going to focus on our summarization product, Omni. It's actually our flagship offering, and there's a ton we have actually learned from it that I'm kind of excited to share here. Essentially, what this model does is take a detailed radiology report, like the one that you see here, and distill it down to what is important. So this is a made-up example to illustrate what I mean and exactly how Omni works. So this report basically has title and some important findings that the radiologist has dictated. And the final impression just says that it's a normal radiograph of the left hand. These summaries are what are called impressions in radiology. Now, as you could see from that impression, this model kind of solves something called as an abstractive summarization problem. So the generated summaries capture not only the essential findings in the report, but also kind of convey the radiologist's nuanced understanding of what the implications are of these findings. And what makes these impressions kind of unique is their radiologist-specific writing style that is tailored to the preference of these individual practitioners. So the summary that we saw before can actually look very different if written by a different radiologist. All of these impressions that you see here are actually clinically accurate. It's just what the radiologists prefer their language to be. The variations are based on what a radiologist like to see, how long they like their impressions to be, etc. So ML model challenges that we face for our products actually has a combination of these domain-specific challenges and some general ML model challenges. Let's go through some domain-specific challenges first. As I talked about, we require personalization for our product. And what we require is something called broad personalization. We are not really catering to like a small group, but aiming to personalize AI model for like thousands of radiologists. This actually requires a deep understanding of the individual's preferences and practices to ensure that the output of the model resonates with each radiologist's way of writing impressions. This can actually be done by implementing unique machine learning techniques that caters to a specific personalization that you want. There are different ways to do this. You could do user profiling or clustering, meta learning approaches, style adaptation modeling, modular deep learning, reinforcement learning, feature engineering, or like a combination of all of these different methods. Another challenge is adapting to diverse report types. Radiology is not really a one size fits all. Different examinations actually necessitates different reporting templates. So this causes source domain variations to the input for our models, which causes a lot of challenge for the model to adapt to. So our AI models have to be flexible enough to adapt to all these variations, ensuring that they can handle anything from like a standard chest X-ray report to a complex PET-CT analysis. This can again be achieved through different techniques. A strong technique would be to develop models with a modular architecture where different components or modules can be combined or activated based on which report type the model is actually accessing at the point. Another challenge is having specialty and subspecialty precision. So apart from these modality level changes, the field of radiology is kind of vast, and anatomy of the patient that is getting treated also matters quite a bit. So this could be areas like musculoskeletal, neurology, urology, any specific anatomy that you want to image on your body. So all of this would require specialized knowledge, and the model needs to be able to understand how to do impressions for each of these different anatomical parts. Our models also need to be able to deal with different age groups. So from pediatric to geriatric patients, the presentation of condition and the interpretation of imaging can vastly differ. So the AI model should be able to process information across this different demographic spectrum and make sure that the model output actually relates to an adult when the report is for an adult, and a pediatric report if it concerns a pediatric patient. So one of the best ways to ensure that we have good performance across these different groups, let it be subspecialties or age groups, is to make sure that we have a really good training data diversity, make sure we cover all the edge cases, all the edge groups as much as we can when training a model. Another important challenge that we have is sub-second impression generation time. So the goal of Omni model is to offer insights quicker than dictation by a radiologist. So that would mean that you need to have high accuracy, but also really, really good speed in a way that matches or even exceeds the current standards in radiology to ensure that radiologists adopt it willingly. No radiologist will want to slow down their daily process just because they're trying to use a tool. So this can actually be done by different methods. So we try to optimize our AI model architectures for speed without sacrificing accuracy. These involve simple steps like reducing the dimensionality of input data, employing techniques like model quantization, pruning, leveraging high computing resources can also help really in reducing the inference time. So apart from these domain-specific challenges, there are also some general machine learning model failures that are actually quite challenging to us because of the kind of data that we deal with. These model failures can actually stem from a variety of causes, often related to data, the model itself, or even the deploying environment. Identifying these potential pitfalls early on during the development can help in creating more robust machine learning solution for the product. So some of the common frequent cases of model failures that we see and the usual strategies we use are as follows. So let's say one of the challenges is poor quality data. So this would be incorrect, incomplete, or biased data that is used for training the model that can lead to poor model performance. The way to remedy this is to implement rigorous data cleaning, data pre-processing strategies, as well as augmentation strategies. This ensures diversity and representativeness in the data set to avoid bias. Another common thing is bias and variance. These are just fancy names for overfitting and underfitting. So the model might perform really well on training data, but poorly on unseen data. And this is mostly because most of the time it's because the model is too complex for the task. So using techniques like cross-validation, regularization, pruning, or maybe just ensuring that the model complexity is kind of appropriate for the problem and the amount of data available. And when when there's underfitting, the model is kind of too simple to capture underlying patterns of the data. The simple solution is to increase the model complexity, or maybe consider things like feature engineering to create more informative output and make sure that you're training sufficiently. Next problem is lack of generalization. The model might perform well on, fails to perform well on new or unseen data due to over-reliance on training data characteristic. An easy way to mitigate this is to make sure you have a well-diversified data set for training and validation. Just try to employ techniques like domain adaptations when applying model to data from different distributions. Another very important one is improper model evaluation, which can cause a lot of failures and causes challenges in machine learning model training. So if we rely on inadequate or misleading performance metrics, it can give a false sense of model accuracy. So choosing an appropriate metrics that truly reflects the model's performance and the project's objectives is kind of important. Then we have like other issues like scalability, making sure the model can scale really well. And another important one is neglecting user feedback. If we fail to incorporate feedback from the end users, it can lead to models that are technically sound but practically unusable, especially in a space like healthcare. To effectively navigate through all of these challenges, what we actually do is come up with some key values that can help us measure how good our ML model is, and then go ahead and evaluate them. So once we can identify these key values, we can identify and establish precise metrics that can rigorously evaluate the performance of these models against these key values. So 3 key values that we had identified for our summarization task for radiology was personalization, clinical accuracy, and fast inference. Like personalization can be measured using some n-gram-like metrics like BLUE or Rouge. So n-gram basically refers to like a continuous sequence of n items from a given sample of text or speech. So this can be letters, words, or like some pairs of data. So these metrics evaluate the generated text by the model by comparing it to n-grams of the model output to those of a reference text, which in this case is the radiologist impression. So basically you are comparing words in the model output to words in the actual radiologist impression to make sure the words that radiologists use is what you see in the model output for this radiologist report. This kind of gives us a sense of how good the personalization from the model output is. For clinical accuracy, because it's a very difficult thing to measure, we have developed our own in-house metric that can capture usually everything we want to look out for as far as clinical accuracy is concerned, make sure all the important anatomy is covered, etc. Fast inference can be measured actually by calculating the model inference time across a variety of input-output lengths that the model actually faces. So given that we have all these metrics and we calculate quantitatively how good these metrics are whenever we train a model, sometimes these general statistics can fail to reveal how failures are distributed across different case types, attributes, or scenarios. So granular testing is something that we definitely do that can help with something like this. But before any sort of such rigorous testing is done to identify rigorous testing is done, we actually need to identify what are some common failure modes that can come up in our output. Some of these are like content omission, where we omit critical findings that have to be in the impression, but the model has overlooked that. Content fabrication, these are things like hallucinations that are kind of common with large language models. Poor coherence, where the radiology reports are quite unclear. There could also be like a repetitive phrases in impression, sensitivity to input length. Radiology report, the model might perform well on short radiology reports, but might not do well on longer radiology reports. There could also be entity recognition error, left being recognized as right or vice versa, that can cause errors in our model. So kind of understanding these domain-specific failures that can happen in your model output is also kind of important before you go into granular testing and take a look deeply into your data. So once we've identified the metrics and the common failures, we do additional granular testing. Granular testing of outputs involve dissecting the results produced by the model to ensure accuracy and reliability and relevance across various dimensions of the input. This sort of detailed approach to testing actually helps us identify specific areas where the model might be underperforming or exhibiting bias, ensuring comprehensive quality assurance. This is especially great for diverse data sets like radiology, where a model needs to work well across all categories of data. We need good performance in radiologist personalization, so we need good performance across radiologists. But along with that, we also want to make sure that diversity in the training data does not affect the model accuracy. So we need the model to perform well on X-ray as well as PET-CT. Similarly, we want the model to perform well on musculoskeletal imaging as well as whole body imaging. So granular testing kinds of helps us go deep dive into how the performance is in each of these subsections and identify failures associated with the model. Yeah, that's all I have for the presentation. Thank you.
Wonderful. Thank you very much, Anjali. So we're going to move to a Q&A format now. I'll be asking some questions to start, but for anybody in the audience, please feel free to use the Q&A widget here in the webinar to post some questions, and we'll get to those towards the end of the talk here. I'm going to go ahead and bring up my screen again. Great. So Anjali, you touched on this already, but I'd like to start with this question about feature selection. So how do you approach feature selection for your models in order to maximize performance?
When it comes to something like feature selection to maximize a machine learning model performance, actually, we really lean into domain expertise first. I think having a solid understanding of the field you're working in actually helps you pinpoint which features are likely to make a difference right from the get-go. And this needs to be decided before you actually start working on the product. So this sort of deep dive into domain knowledge isn't just about picking what the obvious candidate features are for the model to perform well. It's also about uncovering those not so obvious connection between features that might not really jump out at you with that expert insight. Sometimes relying on the machine learning model to make these connections on its own might not be that easy to do. The model might not be able to do well unless you have such a strong data set that you're giving it to. So I would say we approach feature selection from a domain knowledge point of view, try to work along with the radiologist to understand what exactly could make a difference in the model's output.
Got it. What is your process like for working with the radiologist to figure out these features?
So Rad AI is kind of unique in the fact that we actually have a lot of radiologists working in the company with us who actually play a big role in helping us understand our models and also model testing. So we have qualitative evaluations for our models very frequently where radiologists go through our model outputs and kind of tells you where it is going wrong, where improvements are possible. We kind of take that information in and kind of drill it down to understand what exactly in the report can help us make that correction. And we add additional, it could be things like, age, something simple as the age of the patient. Can the age of the patient actually help us produce a better impression? That's something a radiologist can kind of help us understand.
Got it. Yeah. So you have internal subject matter experts that you're able to leverage.
Yes.
Right. Yeah. Great. Thank you for that answer. When it comes to model selection, what kind of criteria are you using?
That's a really good question. So I think for us, when it comes to choosing the right model, it's about finding that sweet spot between reliability of the model and efficiency of the model. So we often go through several rounds of testing different models and setups to see what actually works best for a particular application. It's kind of like an iterative process, but it ensures that we're making informed decisions rather just selecting a model. So this is how we usually break it down. First off, actually, we look at performance metrics. So whatever model architectures you're kind of playing with, you need to understand how accurately that model predicts or classifies based on our specific goals. But it's not really just about accuracy. We also need to understand what specific metrics can help us understand whether the model is actually doing so well. So one thing would be how well a model actually does on your performance metrics. The second thing would be understanding how complex the model is and scalability. So with more complexity of the model, you might get a higher accuracy, but there's actually a catch. More complex model can take like ages to train, and they're also at like a higher risk of overfitting. When they perform, overfitting is when they perform greatly on the training data, but not so well on unseen data. But simpler models, on the other hand, might train fast and are generally more straightforward to understand, which can be a big plus. But choosing that model complexity rightly based on the kind of data that you have and the training time you are able to provide, or you're able to set aside for training this model or running experiments is kind of important. And I think another thing is scalability. So we need models that can gracefully handle like growing amounts of data. So customer base is going to keep growing. That means data is going to keep growing. We want to make sure whatever model we have, as we increase the amount of data that we feed into the model, it's not going to stop working, right? So whether it's during training or when making prediction, the model needs to be able to work well, especially for applications like ours where the data just keeps on coming. Another one would be like something like computational efficiency. Efficiency is like really important, and that could be something like how long it takes for the model to train, but also how quick it is at inference time. You don't want to take like a humongous model and train it on a lot of data, but then the inference time is going to be 5 seconds for an impression generation because the model is so humongous. You
Mhm.
need to consider that as well when, at least in radiology space, when you're trying to implement an automation product into the radiology workflow. Also, resource requirements, the computational power you need to actually train this model and the computational power you need to deploy it in your production environment are like big consideration. So it's basically about understanding what are these different criteria that you need to satisfy before selecting a model. So there's performance metrics. Your model needs to perform well. It needs to be scalable. It needs to be of the right complexity. So it's about balancing all these factors to kind of ensure that the model is reliable and runs really well. Yeah.
Right, right. Yeah, you mentioned you need to get sub-second inference, and so
Yeah.
having a more complex model would make that impossible. But you, of course, still want it to be complex enough that you're doing a good job on the performance metrics, that it's generating a good impression so that your radiologists are happy. I'm curious, follow-up there. So when you're looking at these performance metrics, are you doing that at a subclass level where you're looking across different strata of your test sets?
Yeah, so, radiology is a very finicky space because we're dealing with healthcare data. Any sort of small errors that can actually propagate, that actually propagates into production environment is really, really bad. So we actually employ a lot of testing, a lot of granular testing as well when we test our models before we push it to production. So this would be making sure none of the users that we're training for, every single one of them, none of them actually has a regression. But on top of that, things like how well the model performs across diverse data types. For example, you can maybe on a higher level divide it as modalities or like the X-ray imaging type. So it could be X-rays, it could be CT, MRI, PET CT, etc. Does the model perform well in each of these individual categories? Again, within these individual categories, there are subspecialties. Like anatomy, does it do well in each of these subspecialties? We also further drill down to input length, longer input length versus shorter input length. How does a model perform in each of these individual cases? So we actually test, I think, every single aspect as much as possible
Mm.
during using our test cases before we actually move forward with deploying the model.
How do you decide where to compromise if you are, not performing as well in some subclass, but you're struggling to get performance to come up to match? How do you decide what's most important when you're selecting a model?
Yeah, so it kind of depends. I think one of the main measurement of how well the model is doing in production is actually how much time it takes for a radiologist to actually edit.
Hmm.
So sometimes a long report, like an MRI report that has, let's say, the model needs to output like 1,000 tokens, right? The accuracy, let's say, of the model is not really that high, but such a complicated report, the radiologist actually already need to spend a lot of time dictating it. It can still save him some time if they use it. So even if there are some errors in such long reports, it depends on what sort of errors there are. If there is a clinical inaccuracy, obviously we will not be pushing the model. But if it's just, small stylization errors, then it's something the radiologist can easily correct before moving forward to. So it's kind of like a balance. You need to make sure clinical accuracy is always really high, but sometimes some exam types, because of lack of training data, or maybe we haven't gotten enough examples from the radiologist for that exam type, it might not
Hmm.
do so well. So it's also about what is important for the radiologist.
Right. Yeah, I wanted to follow up on that as well. You mentioned in your presentation about getting feedback. What's your feedback mechanism like? How do you get that feedback from those radiologists?
So we have multiple levels of feedback. One is we have a customer facing team that actually gets manual feedbacks. But on top of that, we also have a really strong production monitoring where we constantly look for feedbacks and see if there are negative feedbacks happening. If there are any sort of negative feedbacks that are recurring, we actually make sure we push that radiologist for a retrain and make sure that that sort of problem is kind of fixed.
Mm-hmm. Got it. Great. Cool. Next question I have for you. In your experience, what are some of the early indicators of potential model failures that you've learned to identify?
Yeah, that's kind of a really insightful question. So when we're working with, AI machine learning models, we often run into some telltale issues that hint at potential troubles that can pop up in production. So it's something that I've already talked about in the presentation is high bias and variance, right? These terms usually get thrown around a bit, but it's kind of important. High bias is like a fancy way of saying model might be too simple. It's like trying to use a one size fits all when what you really need is a tailor-made solution. So the model might not pick up the nuances in the data, which is called underfitting. On the flip side, you have high variance or overfitting when the model is too eager to impress. It tries too hard to fit the training data that it ends up catching all the noise along with the signal, making it a poor performer on any new data. So if you see inconsistent results across your training and test data set, that is kind of a really good indication as to how well your model is doing. So which makes it kind of important to ensure you have a validation data set, and in like if you can really, really do it, even have a test data set specifically set aside for testing to make sure that, potential model failures are identified kind of early, because low performance on testing data set with a decent performance on training data set is always a really good indication.
Mm-hmm.
I think another important thing could be slow convergence during training. Sometimes it would feel like it's taking forever for the model to get its act together, and that's usually a sign of that something's off. Maybe the model architecture isn't quite right, or perhaps the settings that we're using to train it, like most probably something like the learning rate needs a tweak. So you're not hyperparameter tuned really well. So if your model is taking too long to converge, that's actually kind of an indication that something is really going wrong in the way you're training your model. You need to reconsider either your architecture or your training strategy.
Mm.
Yeah. So it's basically about, finding that sweet spot, select the right architecture, tune it as well as you can, select the right data, and make sure your model is appropriate for the data.
Yeah, I can see you've got a lot of intuition here, presumably built up through experience, knowing how long it should take for a model to converge. Is there anything, rule-based that you're using, or like rules of thumb for any of the processes that you talked about? Detecting these early failures, I mean.
So apart from like testing for this granular level testing in actual testing of the model, we actually employ these even during validation. We kind of look at how well the model is performing on like a validation data set even during training and on these
Mm.
diverse data types, right? That kind of can tell us, where it's like it could be that it's performing, the model accuracy is going really, like the curve is going really, really well, but it's just at zero for like some specific diverse data type. That's probably because, there's not enough data or something like that.
Mhm.
Or it could be something like, you've gone through 4 epochs of the date of training and your model accuracy has like changed by like 0.01 since start. Okay, so that's also like a clear indication that something is really wrong with your model. Yeah.
Got it. Yeah, that makes a lot of sense. Thanks for sharing that. Cool. Yeah, I might have another follow-up on that later, but I want to make sure we get to some of these other questions. The next one I have for you is, in your experience so far, can you recall a time where your testing framework, all the testing that you've just talked about, revealed something unexpected, or an issue that you might not have caught otherwise without a robust testing framework?
Yeah, so we have a lot of metrics that we evaluate on, but again, additional thing is we started using Kolena a couple of months ago, and with Kolena, the level of analysis that we can dive into is really, really much more than what it was before. So we are able to kind of pinpoint exactly which group or reports need a bit more fine tuning. And with the Kolena Studio interface, understanding and streamlined spotting of potential issues has really facilitated aligning the team on our model performance. So we actually used to do rigorous testing even before, but this kind of drills it down even further. So we are in a constant state of refinement with our models, right? Always monitoring metrics to decide when it's time for a retrain or something like that. So before Kolena came into picture, comparing these model versions to see what is going well, what is going bad, was actually a manual slog through scripts. But because of there's this diff feature that you can see in Kolena that kind of tells you what the difference between two different model versions on a particular report is. And that's kind of helped us quite a bit. So to answer actually this question, since we have started using Kolena, there have been a couple of instances where we have revealed, like we have seen like some unexpected issue early on during testing before it actually hit staging. So one example was one of our data engineers actually was working on an a model that's used for like it's not a production model, but it's a model that we use in-house. And while testing, he actually realized that some outputs were being truncated when the response are really long. This is something that a metric or a mean or a median or even standard deviation or anything like that cannot actually tell you, because these sort of examples happen very rarely and it's really difficult to catch. But having that granular look into exactly where things are going wrong actually helped us in understanding that, we were not setting the maximum output of the model quite accurately. So that was like a really interesting find that we had recently with testing.
Yeah, that's great to hear. That's exactly what Kalena has really helped to design to help people catch it. It's great that you're able to get a lot of value out of that. Breaking things down into, these subsets is exactly what our founders encountered in their own ML experience. And so, yeah, seeing that mirrored here makes a lot of sense. As far as well, I'll get into that in a minute. I'll just move on to the next question first. Do you have any sense for how much time is saved by preventing regressions from hitting production because you're able to catch it during your testing?
This is it's something like a little difficult to quantify. We actually do a lot of regress testing. So regressions hitting production rarely ever happens. One important thing though is we have managed to drastically cut down the time that we spend on model testing. So there's no longer any manual part to this. Everything is kind of automated through Colina. So the amount of time that we actually spend just on model testing before we deploy to market is like really low. We actually scaled up all our pipelines recently, which resulted in our model testing pipeline time going from 2 weeks to just an hour or two. And Colina wasn't like an integral part of this. So I think by if we rarely see regressions in production, and if at all, these are like really small that requires hot fixes. But I feel like having reduced this testing time is actually quite beneficial in making sure the time that machine learning engineers can actually spend their time doing something more complex than continuously testing models.
Right. Yeah. And I would think that it would help feed into scaling as well. So if you as you scale up, you don't have to have a linear input of effort to be catching all of these things.
Definitely.
Does that sound accurate?
Yeah, sounds
Yeah.
accurate.
Yeah. Great. Great. Yeah. Thank you for that answer. So you have a very diverse user base. You have thousands of radiologists. Each one of them has a slightly different style. You showed some examples of how the same basic information is written differently by different radiologists. So what is your strategy for evaluating accuracy across a really diverse user base?
Yeah, so I think it's to measure this accuracy, it's mainly about picking what right evaluation metrics that you should use. So we need to have the right tools to measure exactly what we are expecting to see. We have to make sure, even though we are personalizing our model, the model still meets all the broad requirements, that it still does well in generalization, even though we are personalizing to individual radiologists. We don't want a new radiologist to not have an optimal performance just because it's not really, a personalized model for him. So it's basically about finding the right metrics that can let us gauge the performance of a model on both a broader, wide scale as well as an individual level, and making sure we balance all of these metrics really well, so that we don't drop personalization accuracy just because we want a wider performance across different data types, etc. Yeah.
Mhm. And as far as the metrics that you're using, are you using your own custom metrics?
Yeah, so we use a bunch of metrics, a lot of metrics actually. Some of them are custom metrics specific to the radiology task. So we have developed these in-house to measure the models. But on top of that, we also use metrics like in-gram metrics like Blue, Rouge, um, embedding, BERT embedding score, etc., to
Mhm.
kind of understand how similar the model output is to a radiologist impression.
Got it. Yeah. Great. Yeah. If we have a moment after this, I'll try and show what that might look like, comparing some of those blue and rouge scores on a data set.
Awesome. Yeah.
Cool. So I'd love it if you could describe the challenges you have with regards to scalability. We touched on this a little bit already, but given that you have to scale while maintaining your models at this high level of accuracy and adapting to this diverse user base. So what kinds of challenges are you dealing with there?
Yeah, so each radiologist has like their unique way of working. So, and the model needs to adapt to these individual style and preferences without actually losing its effectiveness across various exam types. It's actually a challenging balance to strike, but it's crucial for making a model that's both personal as well as widely applicable.
Mhm.
One strategy that can help manage this is actually carefully choosing model architecture and data. So we can use an architecture that allocates parameters specifically for generalization and some other parameters specifically for personalization. So this kind of can ensure that the model remains flexible enough to meet individual needs while still serving a broad range of applications effectively. So then there's a matter of performance consistency. So as we
Mhm.
scale up and we add more doctors, it's imperative that the personalized version maintains its accuracy and performance, no matter who the user is and no matter how, when the last model update was. So to achieve this, we kind of rely on continuous learning mechanism, have feedback loops, understand if when the model is regressing, and if the model is regressing, what can we do to improve it? So we have systems that allow models to update in real time, adapting to new information without actually losing the balance and effectiveness.
Cool. Oh, that sounds very cool. Um, Last question here before I open it up. By the way, everyone, if you have a question, feel free to drop it in the Q&A. We'll come to that in a minute. Has Kolena, so using Kolena as a tool, the tool of systematic testing, getting down to these subsets, has it changed how Red AI views the role of testing?
Yeah, definitely. So since we have personalized diagnostic solutions, we have to meet the needs of thousands of users with their own distinct approach. But maintaining quality is kind of like our top priority. So the trust that our customers have on the product is kind of paramount, and it kind of hinges on our ability to deliver consistently accurate and high performing model. So to ensure that we are always providing the best model, we have to routinely update the models and continuously test it as rigorously as possible. So
Hmm.
this sort of and I think over the past year we had like an exponential growth in customer base, and this growth kind of meant that apart from scaling up our models, we also had to enhance our evaluation pipeline at the same speed. So in order to make sure even the smallest regression does not make it through our users. So that's where Colina kind of actually came in and has been a game changer for us. Colina actually provides these tailored test case driven evaluation framework. So imagine testing on millions and millions of data points, it becomes difficult as you scale up. So having these test case driven frameworks that includes all these customized metrics that we kind of want to use can help us catch and fix some potential issues that are even before they actually reach deployment. So
Hmm.
with Colina, we are able to actually drill down on the specifics, right? To manage the wide variety of radiology reporting style. Where is it going wrong? Is
Mhm.
there a user for which for whom like we are experiencing some sort of regression. And even if we are facing regression for that user, what specific exam types are we facing regressions for? This was something we did not, we kind of were able to do it before, but it just involved a lot of manual scripting and difficulty sharing the results across teams, etc. But I think with Kolena, we are able to do this much more efficiently and effectively, making sure we don't actually miss any sort of test cases just because we haven't included in our scripts or we haven't written up a script for that.
Right.
And I think the interface that we have actually helps in improving the collaboration and alignment across teams. So the machine learning team conducts all these evaluation, but this has to be shared across multiple teams so that people can take a look at, what is the model that is currently being served. For example, customer facing teams would really like to know, if there were any changes in the model that they need to be aware of. So sharing these results were also kind of difficult to do, and it was not always done. But I think with Colina, this sort of collaboration became really easy. So it kind of helped us in making the entire company kind of up to date with what are the changes that went into the model and what sort of improvements we're actually seeing across all of these exam types of users with this new model change.
Yeah, great to hear. I love to hear it. One of the reasons we're excited to have you on this webinar is because you're using the platform so well. You're getting all the value out of it that we're trying to provide and really turning that into, this internal alignment, being able to identify all these different subclass performances, all this stuff, and doing that more efficiently. So I love to hear it. I love to hear it. Thanks for answering that.
Okay.
I guess I do have another question here. So, how has implementing your testing methodologies with Kolena impacted your time to market for new models? I don't know if you have as much insight into this, but I'm just curious. We touched on this a little bit about, the speed of being able to deploy faster because your testing process is faster.
Yeah.
Does that capture it, or is there a little more there?
Yeah, I think that kind of captures it. It's more about how much were we able to save on testing time that we were able to use for something else. So, testing is like kind of like the final step of model training, right? You test and you make sure there are no regressions and then you push it to production. Reducing that window of testing can actually make time to market much quicker. So that's kind of, I think it's kind of the same answer that I gave before, but just to reiterate it, it's when we reduce the testing time, we are able to push to market quickly. That would make the product available quicker. That'll also reduce kind of the burden on the engineers who are trying to, run these tests and spending time getting these tests done.
Got it. Yeah, thanks for that answer. That makes a lot of sense. And we're talking about Kolena here, but I think, you would see these benefits with any truly end-to-end AI quality platform. It's just that they don't exist in the way that Kolena does. And so it's great to hear that Kolena is having that kind of impact. And that's what we're hoping for.
Awesome.
I guess I still have more questions than I realized. If we have some time here, so we'll be okay. What are some of the key strategies that help your team streamline the model training process, testing process?
So when you talk about streamlining model testing process, I feel like that has been a part of continuous improvement for us. So we've just incrementally keep adding things that kind of streamline the testing process. So one is like version control for models and data. I think it's kind of like a safety net. Version control is kind of like a safety net. And it's been a game changer ensuring that every test that we run can actually be reproduced again. So this way we can track every change, grasp what the impact of it, and if it need be, hit the undo button. It's all about keeping things orderly and transparent, and that has kind of helped us in making sure, the process a little bit more streamlined. There's also performance benchmarking. So setting benchmarks to make sure what we expect from our models in terms of our metrics could be just accuracy or blue score, how fast they run, how much computing power they need. We set performance benchmark and make sure the model always passes all of those during testing. In some specific situations, we've also employed automated testing pipelines, like, CI/CD pipelines with some automated testing, just to put us in like the fast lane for testing. The automation checks, the automation test can like flag anything out of line, so we can kind of like focus on the bigger picture tasks.
Right.
I feel like maybe an additional thing is like a standardized test data sets. We use this only for like some specific models, having a go-to collection of test data set to make sure we cover all the broad scenarios with our models and potential quirks in the data, ensuring that the testing is like thorough and content.
Right. Yeah. Thank you for sharing. Last question. I know this one's the last question now. Is there any advice that we haven't talked about yet, just from your intuitions, your experience? There are a lot of different ML teams out there, all kinds of different domains. Based on your experience, what advice do you have for these teams that they're looking to improve across the board?
I think personally, I feel like the most important part of an ML model is actually the data that you're using for training it. I would say always make sure there's quality over quantity. So quality data is the best thing that you can have. Make sure the data is like clean, well labeled, and truly reflects the exact problem that you're trying to tackle. So putting some effort forefront in processing your data right from the get-go can actually make a world of difference to your machine learning model's accuracy. And also kind of make sure that data is kind of diverse so that you cover like all the edge cases to make sure your model does well in all of these different scenarios. Uh, Apart from data, I think another thing would be making sure you select your model really well. Just don't go with the largest possible model you can train, because that's not always the best solution. Select the model appropriately and also make sure you tune it really, really well. So tools like, grid search, random search, or even Bayesian optimization can really, really help you fine tune your model to find the peak performance or to get the peak performance out of it. You need to find the best set of hyperparameters for every single architecture that you're trying to test out. I think apart from that, make sure you're using the right metrics. You need to specifically select metrics that align with exactly what you're trying to achieve. Sometimes we all rely just too much on accuracy. Accuracy is kind of great, but it's not like the be all end all. Depending on the project, the product that you are trying to develop or the project you are trying to test out, you might want to pay more attention to something that reflects exactly what you're trying to achieve a little bit more.
Definitely. Yeah. Yeah. Great. Thank you for sharing your wisdom with us, Anjali. Really appreciate it. Well, we just have one question in the chat here. And then let's see here. I'll go ahead and read it out for you. It says, how do you resolve the platform compatibility issue? You understand that context?
Is this from a Kolena perspective?
I'm not sure. Vina, if you don't mind clarifying what you mean by platform here, that might help us to answer your question. While you're doing that, I do want to show, well, actually, so I'm going to kind of try and summarize what you've shared with us, and then in just a minute, I'll show a little bit of the Kolena interface and what it looks like, just because we can't show Rad AI's data. It's sensitive private health information, so we can't show any of their actual data, but I can show you what it looks like when you're comparing these metrics across different subclasses. So what Rad AI implemented using Kolena as this testing tool, this AI end-to-end quality tool, is a standardized and rigorous model evaluation process. We talked about that. Test case-based solutions, so getting granular about what you're testing. Evaluation metrics, you just mentioned this, Anjali. It's very important to choose the right metrics and to create new metrics where appropriate that match what you're trying to achieve. And then being able to analyze the root cause failures and catch regressions from deploying, so that you're always maintaining a consistent level of performance. The benefits of robust testing in general, you get increased customer productivity, time saved for radiologists in this case. You have a standardization of the evaluation and deployment process. You can start to automation of model testing and deployment. You have an enhanced ability to observe system performance, and you get a more structured and diligent approach to model deployment for all the reasons that we mentioned earlier. So since we have a minute here, let me actually just exit the slide real quickly. This is an example. I'll explain what we're looking at, but this is an example of looking at a data set within the Kolena interface. The way to read this is that each row is a subset of the data. The top row is all of the data. And each of these larger column sections is a model that's been tested on that data. And the individual columns underneath each of the model are the metrics. So this is what we were talking about, choosing metrics that are important to you. So in this case, we're looking at a text summarization problem, so text data. We're using these metrics, these n-gram-based metrics that Anjali mentioned, called BERT, BLUE, and ROUGE. These are ways to try and quantify how well this text summaries, how well these generative models are generating the text summaries. And the value here is that you can see that you get these results, not just for the entire test data set, but you can see how it's performing across different subsets of the data. So in this particular data set, there's something called the business category, and you could see how it's performing relative to the other categories. And you can see where things are regressing in red or improving in green relative to some reference model. And then you can start to automate against this. And what this isn't showing is some of the custom metrics that Anjali's team is using at Rad AI. They have some custom metrics that you can define and basically display alongside of these and evaluate against these alongside them. So I just wanted to show that very quickly to illustrate that. Quick note about further resources. Rad AI has a resource hub, radai.com/resource hub. Kolena has an ML metrics glossary if you're curious about what kind of metrics are relevant for your problem. That's why we created this metrics glossary, so you can come in and check that out. It's on our docs/metrics. And then our blog has a whole bunch of different articles about testing, AI quality, a lot of the topics that Anjali expanded on today. Last thing, I guess, I'll just plug the quality conference we have coming up in June. Feel free to check that out. We'd love to have you. We're going to expand on that more. And yeah, it looks like, Vinay, we didn't have clarification on your question, but if you want to follow up with us, if you want to send me an email, I'm just skip@kolena.com. We'll get that answered for you. Cool. Well, thank you very much, Anjali. We really appreciate having you here today. Really great talk. Good stuff. Good stuff.
Thank you for having me. Appreciate it.
All right. All right. Thank you, everyone. See you next time. Bye.